Okay, so have you ever like actually sat down and tried to imagine how many grains of sand are on a beach?
Oh, man. It's like one of those things where your brain just kind of glazes over. It's too big to really get your head around.
Right, it's just numbers getting bigger and bigger, but you can't really picture it.
You need some kind of like a tool to even start to make sense of it.
And that's where I guess exponents come in, right?
Yeah.
It's like they're giving us a shortcut to talk about those crazy big numbers.
Exactly. They're like a shorthand for the universe, you know what I mean?
I like that. So instead of having to write out, say, the mass of the Earth, which I think the textbook said is 5.97 by 1024 kilograms.
Oh, yeah. Good luck writing that out. You'd be there all day.
Seriously. But with exponents, it's just, boom, there it is.
And it's not just about things that are like astronomically huge. They work on the other end of the spectrum, too.
Oh, you mean like really small stuff?
Yeah. Like the textbook mentions the diameter of a red blood cell, which is something like 0.000007 meters. Imagine trying to write that out every time you had to work with it.
Talk about a headache. So exponents help us, whether we're talking about the mass of a planet or the size of something you need a microscope to even see.
Totally. They give us this consistency, this way to talk about scale without getting bogged down by all the zeros, you know?
It's like they reveal this hidden structure to how big or small things are, a structure we wouldn't be able to see otherwise.
Exactly. It's like a code. And once you understand the code, you start to see it everywhere. Even something like the speed of light, which is what, 300,000 meters per second?
Oh yeah, that's another one that could use some exponent magic. So using exponents is kind of like having this secret decoder ring for the universe.
That's a great way to put it. But there is one thing about exponents that often trips people up, and that's negative exponents.
Oh yeah, those always felt a bit weird to me, like math was doing a backflip or something. Remind me, how do those work again?
Think of it like diluting a drink. Each time you divide the concentration by 10, it becomes less strong, less potent, right?
Right.
Negative exponents are kind of similar. They're a way to express those increasingly small amounts, but in a nice, neat way.
Okay, I'm following so far. So it's like when you zoom out on a map. The further you zoom, the larger the area you see, but all the little details,
Yeah.
they get even smaller.
Perfect analogy. Each time we decrease that exponent, we're basically zooming out, encompassing these smaller and smaller values.
So like 10 to the power of -1, that's like taking just 1/10 of something.
Exactly. And as we go further into the negatives, we just keep dividing by 10.
So 10 to the power of -2 would be like 1 divided by 10 and then divided by 10 again, which would be, 1 over 100.
You got it. It's like using a special lens to see those tiny, tiny measurements we deal with every day.
So we've got these negative exponents helping us explore the microscopic world, just like positive exponents help us wrap our heads around the cosmic scale.
It really shows how cool math can be, don't you think? This one tool, exponents, helps us understand things that are both incredibly huge and incredibly tiny.
Totally. It's like exponents are this bridge between those two extremes. Now, the textbook also talked about these laws of exponents, which makes it sound kind of serious.
Yeah, like we're about to lay down the law exponent style. But really, it's more about, understanding the rules of the game. These laws, they're like shortcuts to help us work with exponents without having to write everything out longhand.
Oh, I am all about shortcuts when it comes to math, believe me. So what are some of these exponent laws? I'm ready to learn.
Well, they are a bunch, but one of the big ones, maybe the most useful one, is that when you're multiplying exponents that have the same base, you just add the powers together.
Okay, that sounds simple enough, but can you give me an example?
Yeah.
Sometimes my brain needs to actually see it in action,
Of course. Let's say we have 2 to the power of 3, and we're multiplying that by 2 to the power of 2.
Okay, I'm picturing it.
So using this law, we can just add those exponents, 3 plus 2, which gives us 5. So the answer is 2 to the power of 5.
And that's way quicker than actually multiplying 2 by itself 3 times and then 2 more times.
Exactly. It's like finding a shortcut through a maze instead of having to walk the whole thing. And believe me, these shortcuts, they get more and more useful the bigger those numbers get.
Makes sense. Now, there was also this term standard form that the textbook mentioned, something to do with exponents, right?
Ah, yes. Standard form, or scientific notation, it's basically a standardized way to write out numbers that are, really big, like astronomically big, or really, really small.
So instead of having a zillion zeros, we can just use an exponent to keep things tidy.
Exactly. Remember we were talking about the mass of the Earth earlier?
That 5.97 times 10 to the power of 24 kilograms.
That's a great example of standard form.
Oh, right. Okay, so it's like it gives us a shorthand that's still really precise.
Exactly. And because it's standardized, everyone knows what it means, whether they're a scientist or an engineer or, well, anyone. It helps us avoid confusion, you
Oh,
know?
totally. I've definitely miscounted zeros before. Not fun. So how does this whole standard form thing actually work?
It all comes down to using powers of 10. Basically, you're writing the number as something between 1 and 10, multiplied by a power of 10.
Okay, can I get another example, though? I'm a bit slow on the uptake sometimes.
Sure. Let's say we've got the number 3,000.
Okay, big number.
To get it into standard form, we got to move the decimal point.
How many places?
We move it 6 places to the left, which gives us 3. And since we moved it 6 places, we multiply that 3 by 10 to the power of 6.
So 3,000 becomes 3 by 10, 6. That's pretty slick.
Right. And you know what's even cooler? If it were a really small number, we'd just move the decimal to the right and use a negative exponent.
So it's like this system that works no matter how big or small the number is.
Exactly. Whether we're talking about the distance to a faraway galaxy or the width of a single strand of DNA, standard form gives us a way to express it clearly and consistently.
It's like we're looking at things from way up high, you know? We can see how big those numbers really are without getting lost in the weeds.
Yeah, it's like having the right perspective, the right tool for the job. And what's cool is, like we were saying, it works for those super tiny numbers too.
Oh, right. The textbook mentioned that, how scientists use the standard form to write out the size of a bacteria. I think it's something like 0.000000005 meters.
And in standard form, that becomes 5 times 10 to the power of -7 meters. Much easier to manage.
Wow, so that's like incredibly small. But we can still write it out in a way that makes sense.
Exactly. Exponents, they're like this secret code that unlocks all these hidden parts of the universe, big and small.
Totally. And I think the textbook ended on a really cool example, talking about those wires on a computer chip, you know the ones?
Yeah.
Like the stuff that makes our phones and laptops actually work.
Oh, right. I think it's that the diameter of one of those wires is only 0.0000003 meters.
Yeah, something like that. Crazy tiny.
And yet those tiny wires, they're essential for, well, pretty much everything we do these days. In standard form, that's 3 times 10 to the power of -6 meters.
It's kind of mind-blowing when you think about it, right?
Oh.
All this stuff we take for granted, streaming, texting, it all comes down to those minuscule measurements, those exponents.
It really shows how everything's connected, doesn't it? Even something as, I don't know, abstract as an exponent, it can have a huge impact on our everyday lives.
For sure. So I guess what we're saying is exponents, they're not just some random math thing. They're a tool to understand the universe, from the tiniest particles to those giant galaxies and everything in between.
Couldn't have said it better myself. They show how creative humans can be, how we come up with these systems to make sense of the world, no matter how complex or how huge or how tiny it is.
Absolutely. And maybe even more importantly, they remind us that there's always something new to discover, something that might seem small but actually unlocks a whole world of knowledge.
Yeah. Well said. So yeah, next time you see an exponent, don't just gloss over it. Take a second, think about what it means, what it represents. You might be surprised at what you find.